It's an immense pleasure for me to welcome you all to this special lecture inserted in the webinar series of the Graduate Program in Physics of the Federal University of Pará in Amazônia, Brazil. I ask everyone to kindly leave the microphone and camera turned off, except for the moment you're going to speak. Questions will be allowed in the end unless otherwise requested by the speaker. The questions can be made using the chat, both in this virtual room and in YouTube. Today, we have the great honor to listen to Professor Phillip James Edwin Peebles, who was awarded with the 2019 Nobel Prize in Physics, together with Michel and Didier Queloz, for contributions to our understanding of the evolution of the universe and Earth's place in the cosmos. In particular, Professor Peebles was awarded for theoretical discoveries in physical cosmology. Our special guest is the Albert Einstein Professor of Science Emeritus at Princeton University in the United States of America. Apart from the Nobel Prize in Physics, Professor Peebles' research on cosmology has been honored with the Eddington Medal, awarded by the Royal Astronomical Society in 1981, the Crafoord Prize, awarded by the Royal Swedish Academy of Science in 2005, the Dirac Medal, awarded by the University of New South Wales, Australia in 2013, and numerous other awards. He has been elected to the American Academy of Arts and Science, the National Academy of Science of the United States, and to the British Royal Society, among various other academies. Professor Peebles is the author of numerous books, including Physical Cosmology, published in 1972, which guided generations of physicists in this field of research, including myself. More recently, Professor Peebles wrote the book Cosmology Century, an insight history of our modern understanding of the universe, on the story of cosmology from Einstein to today, recommended for anyone interested in the subject. Lessons from Cosmology and Sociology on the Philosophy of Science is what Professor Jim Peebles will tell us about today, and I should not make you wait longer to listen to him. Professor Peebles, thank you very much once again for having accepted our invitation, and from this moment on, the audience is yours.
Thank you, colleagues. It's a pleasure to address you. I am not a philosopher. I have spent a long career in physical science, and without really thinking about it, I have accumulated an opinion on the scientist's philosophy of science. I propose to tell you about it and let us see what you think. Perhaps you've noticed that when an interesting idea appears in science, the odds are pretty good that someone else has already suggested the idea independently. It's something I've noticed many times during my career. And I never, until recently, thought anything about it. I've never heard another physicist say that it is rather remarkable that we see these multiple discoveries. Sociologists are quite aware of the phenomenon, realize that as a phenomenon, it has something to teach us. I offer for your attention this paper, published in 1922, by William F. Ogburn and Dorothy Thomas. It's an interesting phenomenon, as you may read, that many inventions have been made 2 or more times. They give a long list of examples, quite impressive. You see continuity of gaseous and liquid states of matter, a remarkable phenomenon, and one that was apparently recognized independently. Kinetic theory of gases, law of conservation of energy, and so on. I was struck by the use of gasoline in automobiles. Otto, when I was an undergraduate, I learned about the Otto cycle in thermodynamics course. Daimler, well, that's a famous name in automobiles. I didn't recognize the name Belden, but that also still is a big name in this field. Well, the authors remark that with the invention of the telegraph, communications is so much better that surely these multiple discoveries will not be repeated. That's not the case at all. We have now orders of magnitude more rapid communication. What it mainly does, in my opinion, is cause people to circulate speculative ideas they haven't thought much about. There is a flood of circulation of ideas going around, typically to be turned into something concrete when someone receives the idea in a form that they are ready to receive. So I propose to explain a modern example in cosmology that has to do with the fact that we are in a space filled with radiation with a thermal spectrum. That is to say, given the temperature, one knows that the intensity of this radiation at every wavelength. Here is an illustration. Each of the data points, a measurement at a given frequency down in the microwave region, the intensity vertically. The solid line you see running over the peak is not a theory, that's measurements done with spectacular precision. And see how wonderfully well these measurements fit the dotted curve that is a thermal spectrum. How did the universe acquire thermal radiation? Surely not as it is now. Space is transparent to radiation. It is not capable of forcing radiation to relax to statistical thermal equilibrium. This surely is as good evidence that the universe evolved from a different state, as is the evidence of dinosaur footprints that those improbable creatures once walked the earth. A deep advance invited in this demonstration of the evolution of the universe. I propose now to take you through a series of ideas that finally led to this discovery. 4 people mainly involved. I put them in alphabetical order. On the left-hand side, Professor Robert Henry Dickey, my teacher here at Princeton University in New Jersey on the east coast of the USA. Next to that, George Gamov, an emigre from Ukraine when it was the Soviet in the Soviet Union. Immigrant at the time of interest here, he was in Washington, D.C. at Washington University. Next, Fred Hoyle, spent his career largely in England at Cambridge University. And on the far right, Yakov Zeldovich in the Soviet Union. Gamov was an expert on nuclear physics when the Second World War started. He was never involved in the weapons programs in the US, I think largely because he was contemptuous of authority, always a good idea. A brilliant, brilliant intuitive physicist, as I'll describe. Bob Dickey, during the war, was working on radar, and in fact, developing much of the technology that would be used to discover this radiation. Fred Hoyle was in England during the war, working on applications of radar, one of the products of work in England, and of course also Bob Dickey and others at the Radiation Laboratory at MIT in Massachusetts, the USA. Zeldovich made great contributions to the Soviet nuclear weapons program. That had mixed results for him. He was awarded for his work in nuclear in the nuclear weapons program. The award, I have it written down here. Oh, where is it? He was 4 times mentioned a hero of socialist labor. He had 4 big medals. When he wanted something from the Soviet bureaucracy, he would wear the medals and get instant attention. But it also meant that he was not allowed to leave the USSR until the USSR was practically gone. He knew too much about the nuclear weapons program. And that had a pretty dire effect on his career, as I will discuss. Now, maybe you could look at these things for a while. these images? Well, I tell you a bit about the ideas that floated around these people. In 1948, George Gamow wrote a wonderfully perceptive paper on the subject of the expanding universe. There had been for a long time the idea that the galaxies are moving away from us, perhaps because the universe is expanding. Gamow realized that if you trace this expansion back to the very early universe, you will have matter tightly compressed together. Degeneracy energies of electrons would tend to force themselves onto the protons or neutrons. You would get a coagulation of nuclear matter that would leave no room for hydrogen, which he knew was the most abundant element. He proposed to get around this first idea, published in a paper famously titled Alpha Beta Gamow. He had a great sense of humor. Beta introduced solely that Gamow and his student Alpha would have a good approximation of the first three letters of the Greek alphabet. For reasons I won't bother you with, this paper was dead wrong. The numbers didn't work to 10 orders of magnitude. Characteristic of Gamow, when he introduced the solution to that problem in his 1948 paper, he mentioned only that in the previous paper there were some numerical errors. It was a dramatically different idea that the universe started out hot. Being hot, the universe would be filled with thermal radiation. In the early universe, when that radiation was very hot, it would thermally decompose any atomic nuclei were left around and force neutrons and protons to be separate. They couldn't coagulate even into deuterium. As the universe expanded and cooled, there would come a critical time when deuterium could form. Once deuterium formed, it could make more complicated atoms by charge exchange reactions. So Gamow had a reason why the universe started forming heavy elements. He could fix the time by the temperature. And knowing the density at that point, he knew that the density and the temperature of density of matter and the temperature of radiation. He could, as his student Alpha later pointed out, predict the temperature of the radiation now in the universe a few degrees above absolute zero. A marvelous discovery. He did this largely by pure intuition, just brilliant. Of course, it may be inevitable that along with his deep intuition and distrust of authority, he was rather uninterested in details. By the 50s, he was talking about other ideas, and his Bain 1948 paper was lost sight of for quite some time. Now, Fred Hoyle knew that back in the 1940s, astronomers had discovered that there is in interstellar space molecular cyanogen, a carbon and a nitrogen atom stuck together. This molecule was observed to be present in interstellar space because you could see its absorption line, excitation from the ground to the first level of starlight. The starlight had an absorption line due to the cyanogen. The interesting thing is that the astronomers also saw absorption from cyanogen in its first excited level. Why should it be in its first excited level? What was knocking it up there? Andrew McKellar at the Dominion Astrophysical Observatory in Western Canada put it that you could imagine a sea of radiation at a temperature of a few degrees Kelvin excited the cyanogen. That observation was pointing to Gamow's sea of thermal radiation. In 1948, Hoyle, with Tommy Gold and Herman Bondi, had introduced a new cosmology, the steady state theory. Hoyle thought that that was an elegant theory, philosophically speaking. He disliked strongly Gamow's hot Big Bang. And so, although Hoyle had the radiation, he distrusted it. Hoyle was also very aware that in Gamow's theory, about a third of the matter would end up in helium through the formation of deuterons that stick together to make the isotopes of helium. the reactions don't go far beyond that because there's no mass 5 to carry past helium. But Hoyle was quite aware of this helium. He at first thought that the abundance of helium in the universe is quite modest, quite small, just about what could be produced by stars. By the mid-1960s, he was fully aware that there is a lot of helium and no explanation where did that helium come from. It was far more abundant than you would expect from production in stars. He was on the edge of admitting that the universe had to have started with a hot Big Bang, but he didn't want to think about it very carefully. If given time, he surely would have. Meanwhile, in the Soviet Union, Yakov Zeldovich was very impressed by Gamov's ideas of a hot Big Bang. It was a little dangerous for him to do that because, you know, Gamov was an emigre from the Soviet Union. They are not popular people in the Soviet Union. And if Zeldovich had been a common citizen, I think he might have gotten into trouble. But given that he was a hero socialist worker, it was all right. However, Zeldovich was of the fixed opinion that the abundance of helium is very low. Since Gamov's theory predicts a high abundance of helium, he thought Gamov's theory must be wrong. You see the sad irony. If Zeldovich had been able to travel to the West and talk to a few astronomers, he would have quickly learned two things. First, that there's a curious excitation of cyanogen, and second, that there is a large abundance of helium. Meanwhile, in the USA, in Princeton, New Jersey, Bob Dickey, one on the left, conceived of the idea of a hot Big Bang for very different reasons. I won't go into the details, just to say that he thought it would be fun if two of the young members in his group, David Wilkinson and Peter Roll, built a Dickey radiometer to see if there is this sea of radiation bathing the Earth. Dickey had invented this radiometer during the war as part of war research. It's called the Dickey radiometer. Somehow no one had thought to build one and look and see what the temperature of space is. After Bob Dickey's first measurement during the war, he traveled to southern United States, Florida, to measure the emission of radiation from water vapor. That's important because once you know the emission, you know the opacity of water vapor. There was great interest in that time in extending radar to shorter wavelengths. But along with those measurements, he used his radiometer to measure what he called the temperature of extragalactic matter. He put a limit of 20 degrees. The experts say that given the motivation and giving the willingness to spend a lot to get a lot of helium for a cold reference load, the radiation could have been discovered shortly after the war, but no one thought to look. Meanwhile, north of Princeton, at the Bell Telephone Laboratories, experiments in microwave communication, the experiments that gave us the mixed blessing of cell phones, caused a problem, revealed a problem. The engineers could not account for the excess detection of radiation amounting to a few degrees above absolute zero, a few Kelvin. The first indication of this was in 1959. For the next 5 years, this anomaly in detection of noise in communications receivers was what you might say, a dirty little secret in Bell Laboratories. At last, two young people at the laboratories, Arno Penzias and Bob Wilson, decided to track down the source of this radiation. They are to be credited for two things. First, they looked for every possible source of radiation locally or in the instrument, and they refused to give up. Management at Bell Laboratories is to be credited with allowing these people to track after this curious anomaly. And finally, Penzias and Wilson are to be credited for complaining about their problem until someone heard and directed their attention to Bob Dickey, whose students were building a radiometer to look for what the Bell experiments seemed to have detected. That led us to the idea of this radiation, the radiation that pretty convincingly shows us that, wow, the universe seems to have been expanding from a hot, dense state. Of course, Hoyle immediately had the helium, along with others. It fits so well. It made quite a convincing story. Now, I must admit, because I came in a little bit in a rush, I forgot to get something. When I was a child, I loved to do things like this. Notice the difference in tone. Relatively high because this is relatively short and you have to fit a quarter wavelength in here. Lower tone because it's longer. An illustration of resonance and of boundary conditions. The universe has a boundary condition not in space but in time. Start very hot and dense, move forward until the temperature is dropped to the point that matter can combine to neutral atoms and molecules. That combination makes a big change in affairs. Prior to that, free electrons strongly interacted with radiation by scattering. Electrons strongly interacted with matter by electrostatic scattering. The result was that matter and radiation acted like a fluid with a pressure that allowed it to oscillate just the way sound waves oscillate. These are oscillations in time, and they have a boundary condition. When the matter recombines, radiation and matter decouple. The result, a boundary condition, is in the next slide. Here, we needn't get into any of the details, except that if you look at the distribution of radiation across the sky in the upper figure, or the distribution in space of the galaxies at large scales, you see these wiggles. The wiggles are the frequencies allowed by resonance, just as the different frequencies are allowed to give you different tones in these bottles. This is well accounted for by a theory of the hot expanding universe that involves several big assumptions. First, that the expanding universe is well described by Einstein's general theory of relativity, the new theory of gravity. Second, that there is a lot of dark matter present, otherwise these wiggles wouldn't look the way they do. And third, that there is a cosmological constant. Let's not bother with all these details, but for one exceedingly important detail, general relativity theory. I mentioned astronomers, sociologists' role in this. There has been, perhaps you remember the science wars. They were a big explosive event here maybe 20 years ago, when sociologists started asking whether our science is really objective and true, or maybe perhaps it is instead a construct forced upon students by the elite faculty who must learn by rote the myths that the elite have formed. This caused great consternation among scientists who didn't pause to realize that there is a strong element of truth to this. When I was a graduate student, I wrote the general examinations to test that I was able to go on to a PhD. The examinations required you have some knowledge of all the branches of physics. That included knowledge of general relativity theory, the meaning of a line element, for example. I didn't pause to reflect then, as I do now, that when I wrote those exams and had to learn a little general relativity theory in 1960, the empirical tests of general relativity were exceedingly modest. It's advertised that there were then 3 tests: the anomaly in the orbit of the planet Mercury, the deflection of light around the sun, and the gravitational redshift. The best test of the gravitational redshift then was the redshift of light from white dwarf stars. They're very compact. They have a strong gravitational field. It makes a pretty large gravitational redshift. Theory and measurement of redshifts from white dwarfs agree. There was one famous example, Sirius B. As it happens, the theory and the measurement agreed, but both were wrong by a factor of 4. It's that kind of mess that makes one so compulsive about checking and rechecking for systematic errors. The orbit of the planet Mercury was solid. On the other hand, you know, it is true that Einstein spent 10 years looking for his theory of general relativity. And one of the tests of the ideas he was exploring was whether it would account for the anomaly in the orbit of Mercury. It takes nothing away from Einstein or his beautiful theory to observe that he stopped looking for a newer and better theory when he got to general relativity, at least in part because it accounted for the anomaly. That makes you a little nervous. The best test, the most secure test, was the deflection of light by the sun, but it indeed was really not a very precise test, maybe to 30% or so. In short, I was at the time, as a student, instructed to learn a theory that had skimpy at best empirical evidence. That theory was a social construction firmly endorsed by the elite physicists that we students were required to learn a little bit about anyway, even though it was not a theory that was at all firmly established in the conventional sense. It was the sort of thing that sociologists were complaining about. I had no complaints. I thought it was a wonderful theory. I loved learning it, and it turned out to be very useful. It turned out to be very successful. Without general relativity theory, we would not have a functioning theory of these modes of oscillation of the early universe. It makes you pause and think. But of course, what the sociologists seem to be missing is a spectacular success of physical science. My favorite example, as I mentioned, is the cell phone. I hate the sight of students walking through our beautiful campus staring at their cell phones instead of the world around them. Human nature, of course. But I celebrate the cell phone for its spectacular demonstration of the ability of scientists and engineers to make atoms and electrons and electric and magnetic fields do their bidding in all of the complication of operations that go into showing you images through liquid crystals, showing you sound saved on solid crystals, computations, data, just a marvelous device, and surely not something we would have if there weren't a very firm grasp on physics. We have then a not unsurprising situation. Physics is marvelously effective, but maybe not totally complete. That brings me to my statement of the scientist's philosophy of science, which I presume to speak for all of science, and they may not like that, but I think this is about right. We assume the world operates by rules we can discover. I've never found, well, no, I have, but by and large, it is taken as manifest and obvious that the universe operates in a logical way. Why do we assume that? if you pause and consider that that person's home was struck by lightning and mine was not, why was that? Maybe because I was a better behaved person. Isn't that a reasonable thing to say? In short, much of our chaotic world doesn't seem to be operating by a lot of rules. It seems to be chaotic. Of course, that's a result of the complexity of the rules that we're now discovering. That cell phone shows you something wonderfully complex that is perfectly well controlled by the rules of physics that we now know. That is great support for the assumption that the world operates by rules, but we ought to be remembering that it's an assumption. The assumptions may be of many sorts. Einstein had practically no empirical evidence when he formulated general relativity theory. He had a good precedent in Maxwell's equations. Just go from a vector to a tensor field, with an elegant step. And the tensor is required because he wanted to satisfy local conservation of energy and momentum. But and he had the beautiful idea that gravity is really the acceleration of motion in curved space-time. That I sit here in the chair and I'm pushing down on it because I'm accelerating upward through curved space-time. A beautiful idea, and enforced by the observation that test particles of different kinds fall almost exactly the same acceleration. He had that empirical hint, and he had Maxwell's equations, but he had also a spectacular extrapolation to get to where he was with general relativity theory. That happens. My honest impression is that he set a bad example by doing it, because not all of us can be Einsteins, and even Einstein was not always right in his brilliant ideas. In short, we do physics and physical science by looking at what's happening. We use observations and we explore ideas that might fit the observations. That leads in all sorts of confusion, of course. There is endless arguments about whether this or that observation is right or meaningful, or if meaningful, whether it actually agrees with my ideas about theories. But beyond that noise, there is very solid progress in theories that are credible because their predictions pass abundant tests. I give you, for example, the acoustic oscillations I showed you. In fact, we should pause and admire them again. The curve is the theory. It assumes general relativity theory. It assumes the presence of dark matter that doesn't interact with radiation, as well as the ordinary matter. It assumes the properties of the ordinary matter are what's in the books. And it assumes, what else? The Einstein's cosmological constant, a term that Einstein introduced when he thought he had to have the universe that is static, because it takes nothing away again from Einstein's genius to remark that when he invented general relativity theory and applied it to the universe, he took it for granted that the universe is static. Things may change, but surely the universe is forever. Surely it's obvious, isn't it? Well, of course, it's not so obvious, and in fact, it's wrong. So we have these few assumptions. We have this spectacular amount of data showing by the dots in measurements of these oscillations and their remnant effect in two ways to look at the universe: by examining the radiation as it's distributed across the sky, examining the distribution of galaxies. I might have mentioned that the bottom curve is a Fourier transform of the space distribution of the galaxies, the amplitude squared, the so-called power spectrum. Look at it. It's just amazing that the galaxies have an order in their distribution that matches, with big error flags to be sure, but nonetheless matches the theory based on the few assumptions of the standard cosmology. Then examine the top curve and your mind is blown away at how closely theory and observation match. That is a sort of thing that forces us to add this theory. They call it lambda CDM, the lambda for Einstein's cosmological constant, the CDM for cold dark matter, and of course all the other stuff that is in there, matter and ordinary matter and radiation. The theory is established and part of our canon of physical theory because it passes abundant tests. Now, we're assuming, as I said, that the universe operates by rules, and we're agreeing that these developments of theories that become credible and accepted because they pass abundant tests are adding to our understanding of what the rules of operation of the universe are. But we have to remember that these rules are all approximations, incomplete. For example, in cosmology, we say, well, I'm assuming there is this non-baryonic dark matter. You may well ask, so what is this dark matter? And I have to admit, I don't know. I assumed it to make the theory fit the observations. That's always dangerous, of course, but here I'm making two additions aside from general relativity, the dark matter and the cosmological constant to fit a whole lot of measurements. That makes the theory very credible, but the theory surely is not complete. I think it's crazy to imagine that the dark sector, so-called, the dark matter and the cosmological constant, is all there is. I introduced these terms for simplicity because they were the simplest way to get a good approximation to what I was seeing the observations are suggesting. It turned out that that's a very good approximation, but surely it's not exact. It's just so difficult to believe that the universe was so lacking in imagination that it put in some 2/3 of the mass of matter into a non-baryonic component that doesn't interact with anything and is the simplest thing you could possibly imagine, a gas of non-interacting particles. It's got to be better than that. In short, I would bet all the money I have that there is a better theory of the universe in which the dark matter and the Einstein's cosmological constant are doing something more interesting. And you know, we say that the theory of radiation is so solidly good, and indeed it allows those cell phones to operate so very well. But of course, although we still teach Maxwell's theory of electromagnetism because it's used so broadly, we know it is only an approximation that fails on small enough scales, high enough energies. We have a better theory, quantum electrodynamics, of which Maxwell's equations are a limiting case. Quantum electrodynamics is wonderfully successful, makes lots of predictions that are checked carefully and agreed and confirmed. But of course, it is thought that quantum electrodynamics is a limiting case of unified theory, electroweak theory, and the electroweak theory surely is a limiting case of something else, a theory yet to be discovered. In short, we have approximations at best, approximations to the way the world operates. It has worked very well so far, and I see no end in sight. There are lots of course, one occupation of many physicists is to see how to improve these theories that work so well but are incomplete. And they see no end in sight. They'll be continuing to learn. There is an interesting question, though. Do we have will we reach a final theory of reality? People talk of it. You hear words of the theory of everything, by which they mean simply the final theory of relativity, of reality. Stephen Weinberg was a strong proponent of this. He has a wonderful book, Dreams of a Final Theory. well argued, but in the end, I just can't buy it because it seems to me we establish good approximations to this assumed reality by the process of checking theory and observations, predictions and measurements. It's a practical fact that we will never establish empirically a theory that costs more to check than the world economies can afford. It seems obvious to me we will never reach a final theory, even if there is one or not. I'm willing to imagine there's no final theory, that it's successive approximations all the way down. But if there is a final theory, I don't see how we'll ever know that it is final because we'll never be able to check all its predictions. It's not a bad situation. It means that we have endless employment. Keep finding better theories. So I'll pause there and for discussion.
Okay, Professor. First of all, before we proceed, I would like to ask everyone to turn on their microphones for a huge round of applause in retribution for this wonderful webinar. Okay,
well,
so we already...
I have to remark, of course, this virtual lectures are new to me over the past 2 years, but that's new in my span of life. I just so miss laying my eyes on people who are laying their eyes on me, or perhaps not. It's just not the same thing, but you people have done the next best thing, and I thank you for that.
Okay, Professor, we thank you very much. So as I said, we already have some questions, but before that, let me take the opportunity to give you an idea of the audience you had. So you have more than 100 people looking at you through this, internet thing. And well, obviously, not only the people that are here in this virtual room, but also people that are attending from the YouTube online transmission, the streaming. So we have people from all the 5 Brazilian different regions, north, northeast, center, west, southeast, and south states like Amapá, Pará, Paraíba, Rio Grande do Norte, Sergipe, Mato Grosso do Sul, Minas Gerais, Rio de Janeiro, São Paulo, Paraná, Rio Grande do Sul, and the capital of Brazil, Brasilia, that is the federal district. So, but we also have, obviously, people from abroad attending you, not most of them Brazilian, but not all of them. So we have people from Cordoba in Argentina, you have people from Aveiro in Portugal, and people from Bilbao and from Madrid in Spain. If I missed somebody, please write down the place so that I can tell Professor Peebles about that. Obviously, we have lots of people from our Federal University of Pará, undergrad and graduate students, postdocs, teachers, professors. But we also have people from many other universities, federal institutes, research centers in Brazil, like Cefet, Rio de Janeiro, INPE em São Paulo, Unicamp São Paulo, Juiz de Fora, Belo Horizonte, University of São Paulo, IFT, Federal of Rio Grande do Sul, from Amapá, Bahia, and many places, some of them familiar to you, some of them not. So a lot of people, as I said, that are being delighted with this moment with you, Professor. And so let me, with no further delay, go to the questions. So the first registration for a question comes from Satish Kumar VH, speaking from Rio de Janeiro.
Thank you, Luis. Thank you, Professor Peebles, for the talk. Just to mention, Luis showed your physical cosmology book. So that was the first ever cosmology book I ever touched in my life. And I turned out to be a cosmologist. So I am a living testimony to your good writing. So another thing in grad school, your textbook on quantum mechanics was refreshing because the very first chapter was historical development. So, but nobody talks about history when they teach quantum mechanics. They directly jump into doing some perturbations and things like this. That's boring. And so from this, I can see that throughout your career, you have some soft spot for history and philosophy of science, more than unusual for a physicist of your caliber, to say. But Feynman famously said, like, philosophy of science is for scientists what ornithologists are for birds. My question is about this thing. So you mentioned about the solar system test of general relativity, right? So I've also read your book, Cosmology Century. So these questions are related to that. So we took the theory from like 15 orders of magnitude higher, and I applied it to cosmology. So what was the motivating factor for somebody to do this? Is it a leap of faith, or is it something like what we recently people call post-empirical or non-empirical evidence or science? So please comment on that.
Thank you for those remarks. I do not agree with Feynman's disdain for philosophy. Steven Weinberg has expressed similar disdain. And they're missing part of the story. And of course, history is fascinating. Why did people go the way they did? I spent much time talking about the discovery of the sea of thermal radiation that fills space, because I'm fascinated by the thought, which I should have remembered to mention, that radiation was there waiting to be discovered. Given that our society did not fall into chaos, did not fall into total chaos, given that people could still make curiosity-driven research, it was inevitable that radiation would be recognized. There were so many paths to it, as I described. Hard to imagine that radiation is a story made up by the elite and forced upon students. It's there. And you notice that it was there, and it taught us a lot about the evolution of the universe. I think that is something that happens time and again. We are guided by the phenomenology. Sometimes the guidance is a lot more schematic than in this case, but I think it is pretty clear, for better or worse, the universe operates in a way that we are learning how to discover. Thank you for mentioning the book on quantum mechanics. I love teaching quantum mechanics. Of course, because it has so many wonderful applications, including those in astronomy. Let me see. You mentioned so many interesting things that I'm not. Well, let me make an advertisement. I found myself in recent years deciding it's time to write a book. I don't know why. Having finished the Cosmology Century, which is kind of technical, I have now finished a book that I think is more accessible to the non-scientist on the scientist's philosophy of science. It will be out next spring. You might be interested in seeing it. What else did you say that I liked?
The Richard David's post-empirical or non-empirical thing.
Sorry?
Richard David's, the non-empirical, post-empirical era that we are entering.
You'll be aware that many scientists were very upset by his argument that we are reaching a phase in which theory becomes so complicated that you must change the rules for acceptance of theory. You must, if a theory is well accepted by the experts, then you must accept it as a part of physical science. His example was superstring theory. It's a good example of that sort of thing. The theory is not empirically established, it is non-empirically established to the satisfaction of many who say, surely this is the way it is. I think an even better example in superstring theory is general relativity. As I said, in 1960, the theory had next to zero empirical support, yet you couldn't find an excellent physicist of the first rank who doubted that the theory is right. A favorite example of mine, can I find my book on, well, I have a book. I learned general relativity theory from this book, Landau and Lifshitz, Classical Theory of Fields. Fascinating. This was published, let me see, the date. Yeah. This is the English translation of the second edition of the Russian version published in 1948. This appeared in 1951. Roughly half this book is devoted to Maxwell's equations, developed in exquisite detail, beautiful stuff, and totally solid. Our society depends on these equations. The other half, general relativity theory, logical to put the two together because they are both classical field theories, tensor and vector and tensor. But the second theory had no support, so different from the first theory. Yet these excellent physicists, brilliant physicists, most capable, felt that it is appropriate to put the two together. That is an example of Dawid's non-empirical establishment. It infuriates physicists. It is a real phenomenon. But of course, I've been in communication with Dawid, and he certainly agrees, without experiment, theory dies. It becomes a story, it becomes a fairy tale.
Thank you. If Luis allows, I have one very quick question, last question. Since you mentioned the Landau-Lifshitz, right? Landau-Lifshitz famously has no history, anything in the book, but it's of course physically correct. But Gamow, talking of Russians, Gamow apparently was a very sloppy calculator. Can you say something about that? That's my last question. Thank you so much.
Gamow was a mixture of a spectacular intuitive understanding of physics. He's brilliant. I think maybe it's inevitable that his brilliance at seeing intuitively what physics is implying made him a little uninterested in details. In any case, that was the case. It certainly was detrimental to his career. You just couldn't trust what he would say. Sometimes brilliant, sometimes absurd. And you know, he was a pioneer in genomics. He earlier was a pioneer in nuclear physics, a spectacular physicist, but not interested in detail.
Okay, Satish, thank you very much for your comments and questions. Professor Peebles, thank you very much for your answers. Well, let me just register that I'm very happy to have this copy in my hands that was given to my brother-like friend, Cuban, Jorge Casimeiras, that shares with me the passion to the universe in general and is attending to you. He's also a physicist that migrated from Cuba to Brazil a long time ago. So let me just pass for the next question that comes now from São Paulo for the National Institute for Space Research from Odílio Aguiar. Odílio, would you make your question, please?
Yes. Thank you, Professor Peebles, for your excellent and very clear seminar. I'm sorry, I will jump a little bit out of your main main purpose of the seminar, because I cannot resist to ask you this question. The question is the following. What do you think about the pre-Big Bang scenarios, the ones without the Big Bang, the rebounding universes.
Right. Right. You have seen that I am an empiricist. I pay attention closely to what fits observations. To get observational tests of this. So we come to the question, although it is clear that we have strong evidence that the universe evolved from a dense state, it is natural to ask, what was the universe like still earlier in time? Was there an earlier in time? There are brilliant ideas about what the universe was doing before it could have been described by Einstein's general relativity theory, going under the name, well, among others, inflation and ekpyrotic theories, all kinds of ideas. This is good physics. But I don't understand why positions about these theories are so strongly held, because it is very difficult to test them. And without tests, what am I to believe?
Gravitational waves can test it.
Yes, if we are fortunate and these waves are detected, it will make, for me, a strong case that we have the inflation theory is on the right track. I could mention that the inflation theory is in some circles strongly supported, in other circles strongly criticized as being quite manifestly incomplete. You know, there is a beautiful idea of eternal inflation. The universe can keep recycling through baby universes through all eternity, except it cannot be eternally old. There has to have been a start to eternal inflation. So it's manifestly incomplete. And to some, that is a very bad thing. To me, everything else is incomplete. Why shouldn't inflation be incomplete? That's the inflation theory. And I am impressed by something else. You know, as I've emphasized, we pay attention to theories that make successful predictions. Now, I would put it that in the 1990s, when people were struggling to see how the evidence that was accumulating fit together, the idea of inflation was that the universe is very close to homogeneous because rapid expansion during inflation has stretched everything out. So we're only seeing a tiny slice of the universe, and in a tiny slice, there can't be many density gradients. So we must see a homogeneous universe. This stretching has to have eliminated space curvature, so the universe has to be cosmologically flat, no space curvature. That was a firmly held position in the 1990s. Now there's a lot of evidence that that's the way it is. So in my way of keeping track of the score, inflation is to be credited with predicting flat universes. Now, that is not a very strong statement because the argument that led to that conclusion is endlessly debated today. But nonetheless, it was the fixed opinion of theorists then that surely the universe is cosmologically flat, and now we know that it is cosmologically flat. That impresses me. Of course, gravitational waves, if produced, if detected, would be a wonderful signature. Unfortunately, the theory has a free parameter, the temperature during inflation, that can be low enough that the gravitational waves will never be detected, alas. Can you think of other ways to argue for one or another of these theories of the universe before the Big Bang?
What do you mean?
Well, what evidence would you put for one or another theory of the pre-Big Bang universe?
No, I'm just think gravitational waves will tell us.
If the amplitudes are large enough. to be detectable?
Well, there are some projects like the Big Bang Observer that would detect if the inflation happens.
Well,
would
now
detect gravitational waves from the inflation phase.
we have to be careful. The amplitude of the gravitational waves depends on the temperature, effective temperature of inflation. What is the rate of expansion of the universe during inflation? That can be measured by an effective Hubble constant, which can be converted to a temperature. They're both an inverse. They're both a frequency, and frequency is energy. So it is traditional to translate the expansion rate during inflation to a temperature. That temperature tells you the amplitude of the gravitational waves. The temperature may be low enough that the amplitude of the gravitational waves is small enough that it will be not possible to detect them against all of the noise of the other ways to produce gravitational waves. No guarantee.
On the other hand, if you don't have the Big Bang, you might have a pre-Big Bang scenario which would produce gravitational waves at higher frequencies.
I'm not familiar with that. Surely other ideas about the very early universe will have their own predictions of gravitational waves, maybe even non-adiabatic initial conditions, non-Gaussian initial conditions. For each of these ideas, there will be predictions that may be tested. That is for the future, though.
Thank you, Professor.
Okay, thank you, Egidio, for your question. Thank you, Professor Peebles, for your answer. So the next question comes from an undergrad student from Rio de Janeiro, Igor Moll. He thanks you very much for the lecture, and he asks, could you briefly comment on the, he has no mic to ask the question himself, so he asked me to read it. Could you briefly comment on the relevance of special curvature in homogeneous and anisotropic cosmologies to describe the dynamics of structure formation since the epoch of matter-radiation decoupling?
Well, that is quite a large part of the standard theory. First, you mentioned anisotropy. There are solutions to Einstein's equation that are homogeneous but anisotropic. Space may be rotating or shearing. Those solutions are pretty clearly not a good approximation to our universe because they would cause large anisotropy in the radiation coming from different directions because it would have different redshifts. So we have a limited degree of freedom in imagining what initial conditions could be like. They boil down really to the possibility that there is a near uniform spatial curvature, and that there are departures from homogeneity on small scales that may grow into large homogeneities that may grow into galaxies and clusters of galaxies. The standard theory that's pretty well tested is that, first, as I mentioned, space has no mean curvature, it's flat. I mentioned that was originally taken from an idea about inflation that was considered persuasive. Now, though, we have experimental tests. The details of those anisotropy of the measurements I showed you on acoustic resonance pretty well demand that the universe be cosmologically flat, that there be no mean space curvature. The standard idea is that there are small departures in the early universe. There were small departures from exact uniformity, and that gravity caused these departures to grow larger. Gravity, after all, pulls things together, and that they eventually led to the formation of assembly of galaxies that appear in groups and clusters. This all works out pretty well under the assumption that these departures from homogeneity have a Gaussian near scale invariant power spectrum, that they're adiabatic. And it works well. And the theory is well tested by numerical simulations of how small departures from uniformity would grow larger and larger. They produce pretty credible looking galaxies. The comment about space curvature should be mentioned. As it happens, a small departure from uniformity in the early universe will produce a local curvature of space-time. So one must think of space-time as being slightly wrinkled. These wrinkles, curiously enough, don't change much as the universe evolves. They're built in. They're present, assumed by hand to fit the observations. Where did they come from? There is a theory within inflation, or their formation. We needn't bother with that. Just take it as an assumption, and you find a pretty good approach to what is observed in galaxies and their clustering. I am very taken by the fact that there are anomalies in these predictions of what will grow out of these primeval space-time curvature fluctuations, these primeval wrinkles that are associated with small departures from uniformity. The gravity grows into large departures that form galaxies. Let me just mention something that really fascinates me. Among the large galaxies nearby, most look flat, remarkably flat, rather like a discus, a pancake. Flat. It's quite striking. Some have bulges in the center. Sometimes those bulges are quite large, and sometimes the galaxy is all bulge, ellipticals. But so many of the nearby ones that are large are pretty close to bulge-free. The simulations, I think without exception, make galaxies with pretty prominent bulges. The community doesn't worry about this for several reasons. First, many of the large surveys of galaxies indicate large bulges, but those surveys are based on very poor observations of individual galaxies. They're reduced to just a few bits of information that give you a bulge that may or may not be real. So although they can quote these catalogs of galaxies with bulges, it's not what you see when you look at galaxies close enough to examine them in detail. And second, of course, they're quite right to say, look, we're just learning how to do these computations. If there are bulge-free galaxies, we'll find them. But I wonder if the story is entirely correct. I mentioned, and I strongly suspect that our theory is incomplete, that I imagine the dark sector is a lot more interesting than what we have now. And I could well imagine that details such as those bulge-free galaxies are pointing to a still better theory of cosmology than we have now. Anyway, yes, space curvature fluctuations play a big role, but the mean curvature of space seems pretty clearly to be close to flat.
Okay, Igor, thank you for your question. Thank you, Professor Peebles, for your answer. So the next question comes also from Rio de Janeiro, from Professor Maurício Calvão of Federal University of Rio de Janeiro. Maurício, do you want to make the question yourself, please?
Sure, thank you. Well, first of all, I would like to thank you for your wonderful and nicely off the beaten path webinar. And I would like to recall that I first met you personally in a meeting in the year 2001 at Durham in England, the same year of 9/11. In fact, it happened when we were there. And I remember having a chat with you. I had asked you a question perhaps about the possibility of having a frame of reference, a kind of motion in Robertson-Walker space-time in which the expansion would vanish. Of course, not the Hubble flow one. And I remember, which gave me a solid impression. You're saying, well, this is not a very, very usual question, sort of conceptual, theoretical, philosophical question. And I see now that you have always been very interested in this sort of themes. My question now, following this off the beaten path, would be, what would you suggest for young people as some couple of topics define somewhat authorities for them to invest on related to cosmology or general relativity in general?
Right, right. First, I remember that conference very well for the horrible event that occurred during it, while we were in such a beautiful city.
Mm-hmm.
You ask an interesting question, always interesting. What shall young people do who want to do research in physical science? Do I choose a field that is well developed and that requires fine tuning of details? Or do I choose a theory that is very uncertain, a subject that is open to ideas, requires exploration of many ideas to fit rather schematic evidence, or do I go to something in between? I moved into cosmology in 1964 with great reluctance because there was practically no evidence. And that made me very uneasy. I could see a few things to compute that seemed interesting. And as it happened, as I did the computations, the observations improved, new questions arose, and through my career, I just followed the advance of the subject. Never saw a reason to leave it. If I entered the field today, I would have a choice. There are big projects that are meant to increase precisions of tests. They involve, well, hundreds, sometimes thousands of PhDs in big programs that will produce great advances, I think we can be sure, in tests of general relativity theory and cosmology, and that these tests may well demonstrate to us ways to improve the theory. Exciting prospects. But you know, there is a limitation that a big project of that sort requires an agreement on the basic theory and the questions to be asked. You have to agree on that ahead of time. And then you will test the ideas. You'll address the questions that you agree on. I don't think Einstein would have done well in that situation. And I wouldn't have. I'm not comparing myself to Einstein. I'm comparing my inclination with Einstein's of trying to think about the broader picture. There still are lots of questions along that line in cosmology, and I mentioned one. I'm really fascinated by the pure disk galaxies we see nearby that do not seem to naturally follow from the theory as now formulated. Maybe they will follow from the theory, but it hasn't happened yet. I'm just writing a paper on another odd situation. You know that we live in a group of galaxies that is part of a so-called local supercluster of galaxies, a flattened distribution of galaxies of which we're part. That flattened distribution extends over a well-defined region, and then there are other flattened distributions and clustered distributions of all sorts. But as you go further and further away from us, there are traces of this flattened distribution still to be seen way out to a tenth, the recession velocity, a tenth the speed of light. It's really quite surprising. And it's hard to imagine how this follows in the Lambda CDM model, but it's something that can be checked by numerical simulations. In particular, do a pure dark matter simulation. Don't bother about star formation. It's too complicated anyway. Run an enormous dark matter simulation to see whether or not this alignment phenomenon is ever seen in simulations the way it's seen in nature around us. There are these ideas. And of course, there's the most horrible problem of all: how do stars form? An idea, a problem that's been with us for many years. Data are accumulating, but I wonder if it isn't time to go beyond formation of the first stars, which are pretty well understood, I think, through heavy numerical computation, to a general theory of star formation. Is that feasible with modern technology? It's worth a shot.
Mm-hmm. Thank you.
Okay, thank you, Mauricio, for your question. Thank you, Professor Jim Peebles, for your answer. So the next question comes from somebody that is attending from YouTube, is Glauber Dosch, that's speaking from Federal University of Minas Gerais in Belo Horizonte. He's asking, the questions you raise on the universe being logical or not have been raised, being logical or not, have been raised by David Hume and discussed by Kant and the entire field of German ideologists. Basically, if we accept the possibility of non-logical universe, we cannot do science. Once we find disagreement with our theory, how would we know it's a problem of the theory, or whether nature simply played a trick on us, breaking rules of logic? And he wrote, we have only two possibilities. Either we assume the universe is logical, or we have to assume that we cannot know anything about it.
I fully agree. And thank you for reminding me. I did say earlier that I am not a philosopher. I should have added that I am not a historian. So I have read a little Hume. It never occurred to me, though, to look at his writing in this direction. I shall have to do some homework. In fact, you know, if you sent me an email with the names you mentioned, I would value it. Can I give you my email address?
Okay, no problem. I will leave mine here, and then the person can write to me, and I can forward it to you afterwards, so that we can proceed. Right?
Right.
Is it okay? Okay. All right.
That's good because I've learned something. I should have thought about that earlier.
Oh.
Surely, Pete, you know, it's such a good question. Why do you assume the universe is rational? Of course, the meaning of rational may be adjusted as we do research and discover how the universe does operate. And as you say, if you don't make that assumption, then how can you do research? I think the practical answer is that I very seldom, if ever, have heard someone, a working scientist, ask whether the subject I'm working on operates by rules. It's taken as obvious by almost everyone, almost all the time. And it's a very practical assumption. I do remember there is a remarkable figure 100 years ago named, oh boy, my memory for names was never good, and I've forgotten good old, well, I do remember, yes, what is his name? I have seen writings in which people have pointed out this very point, that you do research because you are assuming there is a rule to be discovered. And that's an assumption of hope or optimism, however you wish to put it. We have to be optimistic. It's an adaptive trait if we are to make progress. And we are reinforced by the fact that we are making progress, I would claim.
Okay, Professor. Thanks, Glauber, for your question. Thank Professor Peebles for answer. So now we pass from YouTube to this virtual room where two people have raised their hands to make questions. And the first person that did that is Giorgio Torrieri from Unicamp. Giorgio, do you want to make the question yourself?
Thank you. Yes, I'm wondering, I mean, since you mentioned that philosophy is a guide to physics, what do you think of the interaction of pure mathematics with physics? The historical example, general relativity, Einstein had to learn differential geometry to implement the equivalence principle properly, and then of course there is Wigner group theory, etc., etc. And today's physics, a mathematician will tell you that quantum field theory is not as well formulated as, Do you think pure maths is more useless than philosophy, or equally useless, or less useless? Yeah.
It is manifest that pure math is very relevant to physical science. After all, it's used. It's not always used with great care, and certainly quantum field theory is an excellent example of a really messy application of beautiful mathematics. We treat these infinities with great courage. Scandalous. Of course, I remember Paul Dirac was scandalized by quantum field theory. It's just not elegant. All those infinities, ridiculous. So it is useful, manifestly. It is perhaps scandalous that we are so careless about it, but we have a good working relationship, wouldn't you agree?
Okay, Giorgio. Thank you very much for your question. Thank you, Professor Peebles, for your answer. And next question from this virtual room comes from the Brazilian cosmologist, Professor José Ademir Salles de Lima. Ademir, do you want to turn on your microphone and make a question, please?
Okay, thank you, Crispino. And also thank you, Professor Peebles, by the great seminar. And my question is very simple. Actually, I have two questions. In 2009, I attended to a workshop, The Invisible Universe in Paris, promoted by UNESCO. And at that time, you presented the concluding remarks of that conference. And I remember that you criticized the idea that in homogeneous would also describe the acceleration, the late time in homogeneous would also describe the acceleration of the universe. And you also manifested a great confidence in the lambda CDM paradigm. I remember your words when you said the universe, the observed universe looks like the lambda CDM model. Always the lambda CDM model is very close to it because this is what we observe. And then I would like to know your opinion 12 years later now, when you have the tension supernova semi-B to the measurements of the Hubble constant. And I would like to know if this tension may represent in the future, in the near future, a change in the lambda CDM paradigm and the idea of a dark sector. And the second point that is more related with your conference today is I would like to know if you still believe that the Lambda CDM, the research program in cosmology, based on the Lambda CDM, may still be considered a progressive research program in the sense of Lacan, the philosophy of science, Lacan, Henri Lacan. I mean, because it seems that we don't have new predictions of the Lambda CDM model. And now we have the tension, the tension related with the value of the Hubble question. And then I would like to listen in broad lines your opinion 9 years after that Congress. Thank you.
Yes, the tension you mentioned is very interesting. You recall we have two ways to constrain the value of Hubble's constant, one through the observations of relatively nearby phenomena, the other by analyses of what happened back when matter recombined and decoupled from radiation. They are different. The degree of difference and the significance is still up for debate, but let us assume that the tension is real and solid, and that therefore we have an anomaly. My opinion on this is based on the thought that none of our theories is complete and absolutely accurate. The Lambda CDM theory is no exception. It certainly is incomplete. It surely is not absolutely accurate. That must mean that we must expect that there are anomalies. After all, if the theory is inaccurate, it means there are anomalies. And one hopes, as usual, that the anomaly offers us a hint to a still better theory. My opinion then is simply that the Lambda CDM theory still is a very good approximation to the world around us, but it's not a complete approximation, it's an approximation. And that the anomaly, if real, is surely an exciting hint to how we can do even better. I should stress that the anomaly is still a matter of debate. Some authors are convinced that the anomaly is real, but others, using other technology, are refining the way to measure Hubble's constant through observations of relatively nearby galaxies. Wendy Friedman in Chicago has made a pretty good case that it's difficult to measure the distance to a galaxy. You need those distances to get the ratio of redshift to distance, which is Hubble's constant. So astronomers continue to look for better ways, still better ways to measure distances. The so-called tip of the red giant branch. Complicated astronomy. I don't attempt to follow the details, but I admire the heated arguments as people debate just how well this new technology is doing at measuring distances, and whether with this new technology, the anomaly may go away. I must admit, I would be a little disappointed if the anomaly went away, were found not to be real, because the anomaly, if real, is a hint to something better. The presence of flat galaxies nearby is another hint, if real. The more hints we have, the better our chance of learning how to do better. There is always the possibility that the Lambda CDM theory is quite wrong. You can never prove that it is not wrong. You can only argue that it fits a lot of predictions. I think the likelihood that the Lambda CDM theory is quite wrong is quite small. I would not, I think that's not going to happen, but I will be amazed if it is not improved. I remember the conference.
Okay.
And I wish we could have conferences like that again.
Okay, Ademir. Thank you for your questions. Thank you, Professor Peebles, for your answers. Just to stress, so the philosophers mentioned so far were the Briton David Hume,
Yes.
the Prussian Immanuel Kant,
Yes.
and the Hungarian Imre Lakatos. But I just received an email from the guy that asked the question, and I'm forwarding it to you promptly in the future. But so next we move to a question that comes from the YouTube from a city called Campo Grande in the state of Mato Grosso do Sul, Vinícius Carvalho da Silva. He has written in Portuguese, so I'll translate it, right? So Professor Peebles, the idea that we need never reach a final theory of reality, is it compatible with the kind of realism proposed by Max Planck, with like the basic philosophy of all natural science? So we approach the real without ever reaching it. So we combine realism with a theory of truth by approximation. So and he complements, in times of post-truth and post-reality, this cultural climate or environment that we live, can it be bad for the formation of new research, can influence negatively the formation of new researchers, putting them away from this realistic compromise?
I mentioned I am not a philosopher, I am not a sociologist, I am not a politician. I'm particularly glad I am not a politician. The example in the USA is just abhorrent. But I should not get into that. Why? Because I have no idea what to do about it. Politics, as we hear it practiced in the USA, in Hungary, in Poland, you know, I can't see
as well.
I can't see, as well? Oh, yes, I guess so. Yeah, well, okay. I must.
We have a kind of time delay of few years, and we hope in all senses. But yes, please go ahead.
Yes. I can only offer one remark. Nazi Germany developed some spectacular technology to send buzz bombs over to drop on England. That was done in a very repressive society. Pure research can thrive in a repressive society. The best example I know of is the work of Russian scientists in the Soviet Union. They had to be very careful. And you know, Landau spent years in jail for being a smartass. But they did great things. But they were sadly limited. We see the example of Yakov Zeldovich, a brilliant physicist, but quite unable to keep up because he couldn't talk to people outside the Soviet Union. Are we moving to a repressive society in Brazil or the USA? I hate the thought, but I don't know. But of course, I am not the person to ask about what to do with people who refuse to think in what I would say is obviously rational ways. How do you address such people?
Okay, Professor. Thank you very much. So thank you, Vinicius, for your question. Professor, we still have some questions. Can I simply go ahead with them?
Of course.
Okay. So the next question comes also from the YouTube, from Alexandre Badonas, from Federal University of Lavras in Minas Gerais. He's asking, do you remember when did you realize that the Big Bang was a better alternative to Hoyle's steady-state cosmology? Was it before the studies about the cosmic microwave background in the early 1960s?
Yes, it was. Before detection of the microwave radiation, I was not at all sure I should trust the expanding universe theory. It had some good arguments in its favor, but the arguments were largely theoretical, very little empirical evidence. I was uneasy about doing research in cosmology because I could see so many options. But on the other hand, do you know, I was so fortunate that after a few conferences, I knew almost all people working in cosmology outside the Soviet Union. A small field. But the detection of that radiation was totally influential to me. I might just mention one simple argument. The standard ideas about cosmology then, in the early 1960s, was that the universe is close to homogeneous and expanding in a near homogeneous way. Why was that assumed? There was a bit of evidence for it, but it was not well published. I was quite bewildered at the assumption. Why should I assume that the universe is homogeneous, uniform? Is it because one can solve Einstein's field equation for a homogeneous universe? That's convenient, but does that make it right? By no means. The radiation, though, had one particular property written obvious right from the start. It is the same intensity to very good accuracy wherever you look around the sky. Why is it so uniform? Well, it's what you would expect if the universe were homogeneous or close to it. That uniformity really impressed me. And of course, the mere presence of that radiation gave me things to study and examine and consider. It gave my colleagues on the experimental side reasons to do more measurements at different wavelengths to see what the spectrum of this radiation is. It was such a transformative event. It didn't convince me that the steady state theory is wrong, but it did convince me that the hot Big Bang theory is interesting.
Okay, Alexandre, thank you for your question. Thank you, Professor Peebles, for your answer. So the next question comes from Giovanni Danieli from a city called Araras in São Paulo. So he congratulates for the great talk. He has also written in Portuguese, and I'll translate. So there are philosophical thoughts and authors that affirm that the human being builds itself along history, transforming the environment in which we live, essentially. So in this sense, which is the perspective for the social transformation that cosmology can give to the society in human relations?
Well, I wish I could give a strongly positive answer. Many non-scientists are very interested in what we are doing in science. And for them, it surely is pleasant to learn of the progress we are making. Many people who are non-scientists do admire this. And I think their lives perhaps are enriched by the knowledge that we can make progress in understanding the world around us, on small scales as well as large. But how do we reach beyond that subset of the population? That's the big question. For most people, I think, it's more important to know what I'm going to do tomorrow, to put food on the table, to keep occupied. Well, what shall I do tomorrow? People have many things on their minds. And for many of our population, I think around the world, Cosmology is rather well down on the list of things to think about. So I cannot offer the great successes of physical science as something that will educate people in thinking logically. It's rather the job of people at universities, as many of you are, better still, the people in your schools, starting at grade 1. Surely, a grade 1, a young child can be taught to think rationally, at least if you behave well, I'll give you this candy. Don't you think you ought to share the candy with your sister? I suppose that's part of raising people. We had 3 girls and we did our best in raising them that way. And I think they're not exactly, well, all right. They're all right. But does my research add appreciably to the general culture of the world? I wish I could say yes. I'm afraid not. What do you say?
Okay, Giovanni, thank you for your question. Thank you, Professor Peebles, for your answer. The next question comes from a PhD student from here at Pará University, Renan Magalhães. Renan, do you want to make the question yourself? Just turn on your microphone.
Okay, thank you. Thank you, Professor Peebles, for the wonderful seminar. My question is, what do you think about the distance from philosophy in the formation of a physics student?
What do I think of the role of philosophy?
No, the distance from philosophy in the formation of a physics.
Well, do you know, I think that if you wish to go into a science, you are more or less, you must focus heavily on the particular topic you have chosen in science. You have a lot to learn to be able to keep up with what's happening, to add to what's known. A little difficult to maintain knowledge of philosophy at the same time. I'm sure some can do it. I certainly wasn't capable of that. It is only as I reached my present great age that I started to ask myself, what are the philosophers saying? And indeed, I found interesting things. I found things that rather distressed me. But for a student to do that, they have to be pretty flexible. By and large, my suggestion is, if you wish to go into a natural science, do it with full heart. And later, as you mature, start to think about what other disciplines might be teaching, could be teaching you about your discipline. To be too distracted by different ways of thinking, well, can be very, very, very stimulating. But if carried too far, can just cause confusion. At least, yeah. For people like me, stick to your job until you've done it well, and then relax and look around to see what you could have learned from others.
Okay, thank you, Renan, for your question. Thank you, Professor Peebles, for your answer. Especially, I give you special thanks because Renan is doing the PhD with me, and well, he's very focused, and I want him to keep this way. Okay, so the next question comes from Igor Mol. That if he may wants to ask another thing, he's not using his microphone, so he's asking, understanding, or for that matter, resolving space-time singularities, do you think it could be a sensible guide to a better theory of quantum gravity?
Oh, yes. Oh, yes. Those who do superstring theory, I think, are still pretty comfortable with the thought that information is not lost in a black hole, but instead the information carried in is then evaporated out, but in a way that carries information in the sense of quantum physics. We can be pretty sure that there are objects that act like black holes. We have a big one in the center of our galaxy. It has all the features you would expect of a massive black hole. Within classical general relativity theory, there is at the center of this black hole a singularity, an infinity in space-time curvature. We take singularities to be an insult to our intelligence, an insult in the sense that we should do better. Surely, nature does not allow singularities. That, of course, is another assumption. How do you know nature doesn't like singularities? Does nature abhor them? We do, because somehow we're convinced that nature wouldn't do such a thing. Let us hope that is right. Well, perhaps not. Let us hope we can find out which it is. Is that singularity real or only an inadequacy of the theory? I'm hoping for the latter, but you never know. Anyway, I do not follow well the pursuit for a quantum theory of gravity. I can say no more on it, except that it's a good topic for research if that's to your taste.
Okay, Professor. So thank you very much. I think let us then move to our last question. So many compliments coming from all around Brazil. Congratulations again for the excellent seminar, wonderful webinar, and such a thing. So thank you very much once again. So one last question from Alexandre Bagdonas from Lavras again. Did you read George Gamov's and Fred Hoyle's popular books on cosmology when you were young? Might they have some influence in your studies in cosmology?
I did not read anything by Hoyle. I did read Gamov's 1, 2, 3 infinity with interest. But you know, until I reached graduate school, I was not very interested in astronomy. I was far more interested in the world around me that I could touch and handle. I have, in fact, it's interesting. I was, of course, well aware of the stars as a child. I grew up in the center of Canada on the Great Plains. On a cold winter night, the sky at night just blazes with stars. It's beautiful. But I never took an interest for some reason in the names of the stars or the planets. I just admired them. I certainly loved to see the aurora borealis, which can be quite spectacular up there. But I was more fascinated, I think, by catching tadpoles and frogs, and such things, rocks. I only learned that I loved physics when I went to the University of Manitoba, and I only learned I love astronomy as a discipline when I got to be a graduate student and then a postdoc and then a whole career that depended so much on astronomy. Each of us has our own life story.
Okay, Professor, and you certainly have a wonderful one. So, but before we finish, let me ask everybody to turn on their microphones once again. We still have a lot of people attending you. I'll let final round of applause. Okay, Professor.
I have not experienced that in any previous of these virtual lectures. And
It's our pleasure.
I find it very charming.
Okay, Professor, it's our pleasure. Thank you very much. All the best for you. Keep safe. Bye-bye.